A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with the maximum volume? So we want to create this rectangular box, and let's make a picture. However, careful, because it's an open box. That means it doesn't have a top. Okay, open box means no top. So what is this gonna what's this gonna have? It's gonna have well, actually, let me have the picture on the side of the constraint part. Alright, so that means, well, this will have, number one, okay, we want to maximize volume, and the volume will be, for now, a function of two variables. Notice, well, yes, technically the volume of a rectangular box would be length times width times height. That's actually three variables. However, the fact that they're telling us that it is a rectangular box, a square base rather, the fact that it's a square base, that means the dimensions are going to be x, they're the same length for a square base, and a height of y. So that means the volume will be, which is length times width times height. This will be x squared y. However, we need a second equation to get rid of one of the variables so we can do the calculus on it. Alright, so that is, we need to they're telling us about the surface area. That's the other piece of information. The surface area equals 108. Alright, so surface area equals 108 square inches. Okay, so, well, how are we going to define the surface area? So, well, the surface area of a cube, if these were all the same dimensions, x by x by x, well, that would have been the area of one single square of one face, and multiply that by 6. That'll be the surface area of the cube. However, this is not a cube. It's only a square base, and well, we have a height other than x. However, also, this box is not to have a top. So that means we have the following. So S, which is a bottom plus 4 sides. Okay, plus 4 sides. So in this case, well, the bottom, which is a square base, that's simply x times x, which is x squared, plus 4 sides. Well, to find the area of a side, I would need to find either the side or that side or the side in the background, but those sides are given by x times y. xy, but don't forget to multiply by 4 because we have 4 sides. Those 4 sides are x and y. And well, we're given the numerical value of S, which is the surface area, that is 108. X squared plus 4 xy. How about we solve for for y in this case? So 4xy equals x squared minus 108, and y equals, I'm going to divide both sides by 4x. That's going to give us x minus x cubed. Oh, wait a minute. X minus Well, you know what, let me leave it x squared minus 108 for now over 4x. We will deal, yes.
When you move it to the other side, will it be negative 4xy?
Negative, actually it would be
Or
108 minus x squared, in fact. All right, thank you. And well, so that's our y. Yes.
Shouldn't it be 2x squared? Because they're getting top and bottom, or are you just getting it?
No, because since in this case it's an open box, it has no top. All right. Otherwise, if we were looking at the entire box, or you're wrapping a gift, well, in this case you're wrapping the whole box. All right. So let's substitute this. Over here. So that will be v of x equals x squared times 108 minus x squared over 4x. Well, we can divide out one power of x here, and that's v of x equals x times 108 minus x squared over 4, which in this case, distributing, that's going to give us v of x 104 over 8, that's 27 27x, and x times x squared, that's 4x cubed. I mean x cubed over 4. So that's the function to do the calculus on. So we're going to take the derivative, set it equal to 0, find the critical values, use the second derivative test to determine whether we are going to have a max or a min by looking at the concavity. So let's find v prime. V prime of x, the derivative is 27 plus 3/4, or rather minus actually, minus 3/4 x squared, and let's set this equation equal to 0 to find the critical numbers. And well, so in this case, solving for x, that's going to be negative 3 over 4, x squared equals to negative 27. We can turn this into positives actually, but let's multiply both sides by the reciprocal of the fraction on the left hand side, which is negative 4/3, negative 4/3. Well, that cancels the 3's with the 3's and the 4's with the 4's. So x squared equals 27 over 3, which is 9. 9 times 4, isn't that a 36? And taking the square root, plus or minus the square root of 36, which is x equals negative 6 and positive 6. However, we can discard one of the solutions, that is the one for x equals negative 6, because it doesn't make sense to have a rectangular box with a negative length. I mean, so that's weird. So legitimately we have only one critical value. So let's go back to find y. Y equals 108 minus 6 squared over 4 times 6. That is y equals 108 minus 36 over 24. So that's going to be, is that an 82, or what's the number here? Okay, let me check my notes. So the y value, okay, no, so 108 minus 6, that's 102, minus 30, is that 72? 72 over 24, and that equals to 3. All right, so the dimensions are 6 by 6 by 3, and that's 36 times 3. Is that a
36 times 3 is 108.
108? So those are the dimensions, and the volume is 108 cubic inches. But again, All we're doing here is just compute numbers. How do we know if this is indeed a maximum or something else? We need to do the second derivative test. So let's find v double prime of x. That's the derivative of 27, which is 0, minus 6/4 x, which reduces to negative 3/2 of x, and evaluating the second derivative at the critical value, which is 6. That's a negative 3/2 times 6, and 6/2 is 3 times 3. That's a negative 9, which is negative number by the second derivative test. This means concave down,
This will be a maximum.
and it's indeed that's what justifies that this is a maximum. All right. And let's do one more example before moving to the next topic. All right. And the next example could be a little tricky at times, and well, I'll show you all the bits here. So, find the point on the curve y equals the square root of x that is closest to the point 3, 0. Well, what is this about? So, number one, let's draw a graph. The graph of the square root of x, 1, 2, 3, 4, 5, 1, 2, 3, okay, 0, 0, 1, 1, 1, 1, 4, 2. So that's the graph of the square root of x. And well, they're asking us about the point 3, 0. From the point 3, 0, which is this point. Well, there's many ways to go from the point 3, 0 to any point on the graph of the square root of x. Alright, one possibility, well, from 3, 0 to this point, that's one possibility. This is another possibility. This is another possibility. So do you see how many ways are there to get from the point 3, 0 to any point on the graph? However, we are looking for the point that is closest. I mean, look at this distance here. This distance from the point 3, 0 to this point is a pretty long distance. This is a shorter distance. This is somewhat a shorter distance. But how do we know which one is the shortest? Well, we can't use the distance formula to exhaust until we get all the points, right? So that's why we are going to use calculus to find that distance. So in general, we'll find out what this distance is in general. I mean, just so to speak, this distance d. All right. Well, so in this case, well, closest, closest in this case, it's another way to say minimum distance. The minimum distance. Alright? So this time we're going to find a minimum, not a maximum. But here is the thing. So what do we know about the distance formula? Well, the distance formula, let's write it down. The distance formula is going to be involved. The distance between this point and this arbitrary point that I'm going to call xy. Because that point, xy, is any point on the graph of x, of f of x equals the square root of x. Any point. So, the distance between 2 points is going to be our x2 minus x1 quantity squared plus y2 minus y1 quantity squared. That's essentially, the Pythagorean theorem. When you find the distance between 2 points, you're finding the hypotenuse of the triangle that this gives rise to. Alright, well, so putting this into context, how about we label this our P2 and this to be our P1, because we need a reference, so we can do y2 minus y1 squared plus y2 minus plus x2 minus x1 squared. Well, x2 minus x1. d equals the square root of x minus 3 quantity squared plus y2, which is just y, minus y1, which is 0, quantity squared. But what's y minus 0? Well, number one, that's simply y squared. So we have two issues here. Number one, this is a function with two variables. We need to make this a function of a single variable so we can find the derivative and find the critical values, blah blah blah. You know the drill for that. And well, okay, let's go ahead and do that. So number one, we're given a y. We're given this y. Actually, this y is, well, actually, let me use a different color. This one. This y right here is the given function. Y equals the square root of x. That's what we're going to replace that with. So that's d equals the square root of x minus 3 squared plus squared, and that quantity squared will be the square root of x. And well, the square cancels the radical, and that's d equals the square root of x minus 3 quantity squared plus x. And this is a function that we would have to do the calculus on. However, check that function. Doesn't that function look a little complicated? We would have to use a double chain rule, an overall chain rule for the radical and an innermost chain rule for the x minus 3 quantity squared. So I'm going to simplify the inside. Number one, I'm going to expand the binomial x squared minus 6x plus 9 plus x, and this reduces to d equals to x squared plus, minus 5x plus 9. Alright, now again, this is still a chain rule problem, and you don't want to deal with radicals and then those radicals that later are sent to the denominator. So here is a freebie. Here is a freebie here. So minimizing d squared is the same, or is equivalent to minimize d. So this is what we're going to do. We're going to square both sides of this equation here. I'm going to write the whole thing again. d equals the square root of x squared minus 5x plus 9. Square both sides. That's d squared equals to x squared minus 5x plus 9. Alright, so you don't want to get confused with this d squared. However, we're going to relabel this d squared. Let d squared equals uppercase d. Let's call it uppercase d to make this a lot simple. So big D equals to x squared minus 5x plus 9. And then that's the function we should do the calculus on. I mean, you can still solve the problem using the radical function. That's going to give you a nasty function to work on. However, this is going to be a lot easier. So this is going to be d prime to x minus 5. That's the derivative. Set the derivative equal to 0. To x equals to 5. X equals to 5 halves. And well, so we have now a critical value. So now we may go back to the original y, which is the square root of x. Y equals to the square root of 5 halves. But the problem doesn't finish there, because we still need to justify that point. So So the point will be 5 halves, comma, the square root of 5 halves. Alright? So we still need to justify that indeed this critical value is a minimum. So find d double prime, which is 2, but check this out. What's the sign of the second derivative there? So what does that tell us about the concavity of the function? Concave up? Because this is concave up. Happy face, what does that mean? Max or min? Minimum. So therefore minimum. Okay, 5 halves, what's that? 2.5? So let's go to 2.5, and whatever that y value is. So this is indeed the closest point from 3,0 to any point on the graph. Well, that any point is actually 5 halves, comma, the square root of 5 halves. So again, whenever you deal with a situation like this on the exam or something, yes, this is going to give rise to somewhat a nasty function to work on, to do the calculus on. Minimizing d squared, it's the same as minimizing d. So square both sides, turn it into a nice polynomial, and relabel this d squared with uppercase d or uppercase r or whatever you want, however you want to call it, or big F, I don't know, or simply little f of x. Yes?
The square on the d, it doesn't matter?
It doesn't matter. Because I mean, if you have something that it's a minimum, square that value, it's still minimum. Alright? Okay, this is the end for this section. So for today we're gonna start doing the reverse. Wait, no, not this one. Antiderivatives. So throughout at least 1/3 of the course so far, we have worked with finding derivatives, doing a bunch of applications of derivatives, like depending on the setting, something like just simple rates of change, you know, how y change with respect x, related rates, optimization problems, differential problems to see what's the impact on the dependent variable by making a minimum or a tiny change on the independent variable. So there were different applications. Now we're going to do the reverse. We're going to find the antiderivatives, which will lead to the integrals. That's the inverse process of finding the derivative. So this is the formal definition here. A function big F is called an antiderivative of little f on an interval I if big F prime equals to little f for all x in the interval I. Alright, what's that going to be? Well, we'll look at the intervals later. For now, let's get a visual of this. So, if the derivative, check this out, if the derivative of x squared equals 2x, that means if we are given 2x, its antiderivative will take us back to x squared. So in other words, we're given a 2x, they're asking us for the function whose derivative is 2x, and we need to think backwards. Well, for a few minutes we will have to think backwards, but that's not going to be easy every single time. So of course we have formulas to do all these backwards processes, you know. So in the same way, the derivative of sine is cosine. If we're given cosine and they ask us to find the antiderivative, that they're asking us essentially what function has a derivative equal to cosine. In this case is sine. So we're going to go basically back and forth between one and the other. However, there is a little downside here with the antiderivatives because, well, so the derivative of x squared is 2x. That's it. There's no other derivatives. A function has a unique derivative. However, A function has infinitely many possible antiderivatives because there's infinitely many possible functions whose derivative is 2x. And well, so that's the question we ask ourselves in here. Does a function have more than one antiderivative? The answer is yes, as opposed to a function having more than one derivative. No, derivatives are unique. For example, let's ask ourselves, what other functions have 2x as their derivatives? What other functions? Well, of course, number one, we have an example f of x, or let's call it big F, because this is the antiderivative, that's x squared. All right? Question over here, yes?
I was going to answer.
Yes.
I was going to say 2x plus 1 2x plus 2 2x plus 3.
Well, we're looking for x squared, okay, another one, big G of x, x squared plus 1. Well, take the derivative of x squared plus 1. What's that? Isn't it 2x? Because the derivative of 1 is 0. What about big H of x? I don't know, maybe x squared plus 73. All right? Well, the derivative is still, it's 2x. Big K of x. How about x squared plus e to the pi? Well, e to the pi is just another number. It's a constant. So, and you can have your favorite integer, x squared plus the cube root of 7, maybe your favorite number, and it's not limited to rational, irrational. It can be anything. All right? Well, because of the situation, because of the antiderivative is not unique, we need to, we cannot write every single antiderivative of a given function. For example, if I ask you to find the antiderivative of little f of x, that's, let me call this 4x. So what function has a derivative equal to 4x? Okay, think backwards. What do you get?
X.
So there's some x squared, right? But times what is going to give me a 4? 2. But that's only one antiderivative. That's essentially 2x squared plus 0, or could be 2x squared plus 5, or could be 2x squared minus 7. Do we really have time to write infinitely many antiderivatives?
No.
We need to express this in a generalized way, and that generalized way is to add a plus c to the antiderivative, which is an arbitrary constant, and that constant is actually to be determined. We will do that later. Alright, we will do that later, but in the meantime, let's work with finding antiderivatives. Alright, so in this case, we're not going to look at the formulas just yet. So let's see, use your knowledge of derivatives to find the most general antiderivatives of the following. So let's find big F. So what function has a derivative equals to 6x? 3x squared. What function has a derivative of 2? But since there's infinitely many ways to get this antiderivative, just add a plus c. Alright, that's it.
Wait, why did you have to do the 2x though?
Because the derivative of 2x equals to 2. Yep. So yeah, we're finding the antiderivative for 2 terms this time. Alright, g of x. Let's find big G of x. So number 1, the derivative of what function equals 4e to the x? Well, I mean, let's think backwards. So what's the derivative of e to the x? Isn't it itself e to the x? Well, so not surprisingly, the antiderivative should be going back in the same, using the same way. I mean, so e to the x, and just write down the 4. However, plus c. All right. Another big F. And careful with this one. The derivative of which function would give us a sign? Alright, so we know that the derivative of cosine is negative sign, but we don't want negative sign. We want positive cosine. To even this out, multiply by a negative on the cosine. Is this making sense so far? You guys following me here? Alright. Letter D. Let's find big F. What function has a derivative? Yes.
Would it be negative cosine x plus c?
Oh, yes. Thank you. Plus c. I forgot the c. Thanks. What function has a derivative f of x equals 1 over x? ln of x. All right. For now, ln of x.
Plus c.
Let's put some question marks over here. We will discuss about this one in a second. All right. But yes, the ln is fine.
You have to do the plus C too.
Oh yes, the plus c.
So on the test, do we just write plus C, or are we going to get to a point where we know it's plus?
Yeah, you will be given a point to find that that value of c. And I'll explain what is this value of c, how do we find it, and what does that represent soon. One more. What function has a derivative 3x squared? X cubed. And I'm not going to forget the plus c this time. Here it is. Now, of course, there has to be ways to get this antiderivatives. And here is a table of antiderivatives which are really integration formulas. So for example, the antiderivative of a constant times a function is a constant times the antiderivative plus c. The antiderivative of a sum of two functions is the sum of the antiderivative. Those are more like the linear properties of these antiderivatives. And well, x to the n, for which we had to guess, like, oh, 3x squared is the derivative of what function. So instead of trying to think backwards, here is what we call the general power rule. Add 1 to the exponent, divide that by the new exponent. Alright? So if we use this formula over here, if f of x equals 3x squared, big F will be 3x to the 2 plus 1 divided by 2 plus 1 plus c. And this reduces to 3x cubed over 3, cancel the 3's, x cubed plus c, which is the same that we got by thinking backwards. So this time we no longer have to think backwards because, again, in some cases it's not that easy. Lucky for us, we have formulas. And well, here is the thing with the antiderivative of 1 over x. The antiderivative of 1 over x is ln of absolute value of x. Alright, let's think of this. So the thing here is that 1 over x, why do we have these absolute values? Because f of x equals 1 over x. The graph of f of x equals 1 over x looks like this. Alright? What's the domain of the graph of f of x equals 1 over x?
Doesn't it depend on which point it is? So it would be from negative infinity to the end point.
Everything excluding 0.
Yes, exactly. So we're looking for the domain, not to the limits. But so that is correct. Everything except 0. That is negative infinity to 0, union 0 to infinity. So we can plug in any value to this function except 0. However, when we go from 1 over x to ln of x, we have an issue with the natural log of x. Because the domain of the natural log function, it's only the set of all values greater than 0. It actually doesn't accept negative values, right? However, when we're doing an antiderivative, the antiderivative of 1 over x, which gives us ln of x, well, what's the domain of 1 over x? Again, all positive and negative values except 0. So these domain properties have to be inherited into the antiderivative of ln of x. Well, what do we do to the ln of x function in a way that it can inherit the domain of the function whose derivative is 1 over x? Well, put absolute value bars so that it accepts both negatives and positives values. Alright, so that's why when we integrate or we find the antiderivative of 1 over x, it's ln of absolute value of x. In some cases later, when we get to the substitution method, I'll show you why in some cases we need absolute value bars and why in some cases we don't need the absolute value bars. But we will discuss that in its due time. Question?
What happens when the x is 0?
When x is 0, so what's the derivative? Okay. Let me when x equals to 0, so for example, you have f of x equals 2, okay? That's the same as saying f of x equals to x to the 0 power. Alright, so the x to the 0 power, it's there in spirit, right? So we just summon its spirit to make it more visual, and we can use the general power rule. That's a 2 to the x to the 0 plus 1 over 0 plus 1. And what's 0 plus 1? 2x. Alright? So actually we did that here where? Here, 2x to the 0 power. It was there, but not there, right? See what I'm saying? Alright. Let's discuss more formulas. Well, the antiderivative of e to the x is e to the x itself. The antiderivative, careful, of e to the or b to the x. So notice to find the derivative of an exponential function of a base other than e, that was b to the x prime. That was itself b to the x times ln of b. So when we took the derivative, we had to multiply by this constant ln of b. For the antiderivative, we have to do the reverse, and the reverse of multiplying is to divide. The antiderivative of cosine is sine, because the derivative of sine equals cosine. The antiderivative of sine is negative cosine because negative cosine prime equals to sine. The antiderivative of secant squared will be tangent, because the derivative of tangent is secant squared, and so on and so forth, and a couple more formulas involving the inverse trigonometric functions. Whenever, I remember when we took the derivative of arc sine or inverse sine, that was 1 over 1 minus the square root of x. So now we're going to take the antiderivative to obtain the arc sine or to obtain the arc tangent. Of course, later we will discuss a lot more of this for the rest of the semester, and we're going to go a lot more in depth next semester in calculus 2. In the meantime,